by Mustafa Bashir. I'm always impressed by how he can cover so many topics that are quite complex in such a simple way. Since I don't have that ability to cover multiple topics, I'm just going to cover one topic, diffusion-weighted imaging. My disclosures are shown on this slide over here. So the objectives of my talk are to spend some time understanding the basic physics of diffusion, to understand basic principles of diffusion-weighted imaging technique, including a little bit about acquisition and optimization, and finally, to spend just a little bit of time understanding basic principles of DWI interpretation, focusing on qualitative and quantitative aspects. You'll see the word basic is showing up on 3 separate occasions here, and so my goal is to focus in on some of the basics. My outline follows directly from the objectives, so let's start by talking a little bit about the basics of the physics of diffusion. So you might ask, what is diffusion? Diffusion is the net movement of particles or structures, such as water molecules, from high to low concentration, as illustrated in this cartoon. Now, it's very important to understand that the motion from the high to the low concentration is due to the random motion of particles. And so we can do a thought experiment where we start with, say, 7 water molecules on the left and 7 water molecules on the right, each in a beaker of water. And due to random motion, the particles will move, and after a certain amount of time, they might end up as shown over here. Now, because this is random, if we were to try to repeat the experiment and have the water molecules in the same exact starting space, they might actually end up in a different location because the motion is random. So this is what we mean by diffusion. Okay, well, there's another term called diffusivity, or D, and what is diffusivity? Diffusivity is a physical parameter. It's a mathematical physical parameter that defines diffusion. It's a marker of how far the particles or the molecules of interest spread as a function of time, as shown on this cartoon. Now, diffusivity has an equation. It's basically the average displacement of these molecules squared over 6 times time. And what I'd like to emphasize now is that the units of diffusivity are area divided by time, or millimeters squared divided by seconds. We'll come back to this later when we talk about DWI. Now, you may have heard the terms free diffusion and restricted diffusion, so what's the difference? Well, let's start again with water molecules in some beakers of water, and let's put these water molecules into different locations. In one example, on your left, we have no physical barriers, and on your right, we do have physical barriers, and let's just do the thought experiment. What will happen to these water molecules if we allow them to diffuse? Well, the water molecules on your left will be able to diffuse through the entire beaker of water, while the water molecules on your right will diffuse, but they will be sort of stuck within their barriers, and therefore the diffusion is considered restricted. So does that mean that diffusion can be classified simply in a binary way, that diffusion is either free or restricted? And the answer is no. In biological tissues, it is a spectrum. Imagine these identical distribution of water molecules and ask, what is the diffusion of each one of these? Well, as illustrated in this cartoon, the diffusion of all these water molecule clusters is the same, but now let's put them into biological tissues, and we can see that depending on the size and density of the cells, as well as the spacing of the extracellular space, we might imagine that water molecules can diffuse more easily over here than they can over here. Fewer barriers, more barriers, freer diffusion, more restricted diffusion. So in biological tissues, diffusion is a spectrum. It's not a binary yes, no. So let's review the diffusion basics, physics. So I explained that diffusion is the net movement from high to low concentration, that diffusion is due to random motion of particles, such as water molecules. Diffusivity is a physical parameter. It is the coefficient of diffusion. We will attempt, as we will see later, to measure the diffusivity, but we're not quite able to measure diffusivity. Instead, we're going to be measuring an approximation of that, and I'll talk more about that later. In biological tissues, diffusion is a spectrum. It's not just binary, it's a spectrum ranging from free to restricted. So let's now move on to basic principles of diffusion-weighted imaging, and we'll talk a little bit about acquisition and optimization. First question is, can diffusion be assessed non-invasively by imaging? And I think all of you know that the answer is a resounding yes. In the year 2021, diffusion can be assessed non-invasively by MRI. To my knowledge, it cannot yet be measured non-invasively by ultrasound or CT, but there may be developments in those modalities that I'm not aware of. Now, does MRI assess diffusion of all molecules in the human body? And the answer is no. Clinical MRI, it's important to make this clear, clinical MRI in the year 2021 assesses the diffusion of water molecules. It doesn't assess the diffusion of fat molecules. It doesn't assess the diffusion of protein molecules. It assesses the diffusion of water molecules. Now, the diffusion of water molecules may or may not be affected by the presence of fat, may or may not be affected by the presence of proteins and other structures, but what we're actually looking at in 2021 is the diffusion of water molecules. So then you might ask, well, how does MRI do this? How does MRI assess the diffusion of water molecules? Well, it uses a special sequence called diffusion-weighted imaging, or DWI. Now, DWI is usually a spin echo sequence, so there's a 90-degree excitation pulse, a 180-degree refocusing pulse, and that generates a spin echo, and gradients are applied in the slice selection direction to select a slice. So DWI is usually a spin echo. But this is not enough to do DWI. In order to do DWI, you need to apply so-called motion encoding gradients, or MEGs, and these motion encoding gradients can be applied in the slice direction, in the frequency direction, and in the phase direction. And as we will see later, they can be applied in all the directions simultaneously, and we'll explain later why that might be helpful. But this is still not enough to do DWI. In order to do DWI, we need to read the spin echo, and we will usually read it using something called echo planar imaging, or EPI, an EPI readout. So let's talk a little bit about this EPI readout. Why do we want to do an EPI readout? Well, the reason we want to do an EPI readout is that it is extremely fast. When we do an EPI readout, a single 90-degree excitation followed by a single 180-degree refocusing pulse can generate an entire image. All of case space for an entire image can be reconstructed from a single 90 and a single 180. And this is very rapid. The entire process can occur in less than 100 milliseconds. So think about that. That's less than 1/10 of a second. Why might we want to go so fast? Well, the reason we want to go so fast is that if we're trying to image the diffusion of water molecules within the body, we want to avoid as much as possible any bulk motion due to, say, movement of the liver or other structures due to breathing or due to cardiac pulsations. So we want to image very fast, and the EPI readout allows us to do that. So that's good news. How does EPI work? Well, let's start again with this spin echo, and this is to some extent just a summary of what Dr. Bashir explained so eloquently in some of his lectures. So we have a spin echo, and we're going to now sample this echo with a bunch of frequency encoding steps. Notice that one frequency encoding step is going up, the next one is going down, the next one is going up, down, and so we're going to zigzag through case space up and down with our frequency encodes. Now, how do we get, though, from one frequency encode to the other? Well, we apply phase encode steps to sort of blip from one readout line to another. And basically, by doing all of this across about 50 milliseconds, we can fill all of K-space with one set of frequency encodes and phase encodes. So what's the problem here? Well, the potential problem is that you'll notice that there are no refocusing pulses. We are doing a lot of phase encoding, and each phase encode imparts phase information and also potentially phase error, but there are no refocusing pulses to correct those phase errors. So as we sample through K-space, as we go from the first point in K-space to the last point in K-space, this takes a certain amount of time, the K-space traversal time. During the K-space traversal time, phase errors accumulate. The longer the traversal time, the greater the phase error accumulation. In addition, and this is also something that Dr. Bashir explained, is that during the traversal time, this is occurring over the course of about 50 milliseconds, signal is actually decaying even as we are collecting the data. And in this particular case, because there are no refocusing pulses, the signal is being lost as a function of T2 star, which introduces blurring, T2 star blurring into the image. So the net effect is that if you do diffusion-weighted imaging with an EPI readout and you spend a lot of time collecting that EPI K-space information, you are going to get a lot of spatial distortion due to phase errors. You're going to get a lot of ghosts, and you're going to get blurring of your images. So these images can be degraded to the point of being unreadable. Now, there are many solutions to this, and most of the solutions are actually belong to the manufacturers. In the interest of time, I'm not going to talk about the multiple solutions that the manufacturers have developed over the last 15 years. Instead, I'm going to focus on the solutions that you can implement in your practice. Very conceptually, if prolonged traversal time causes the error, what you want to do is you want to reduce the traversal time. And how do you do that? Well, you apply parallel imaging so that you skip phase encode steps, exactly as Dr. Bashir explained in his lecture. You also lower the spatial resolution. You do fewer phase encoding steps in the phase encoding direction, and you do fewer phase encoding steps in the phase encoding direction. And the net result is that you have a reduced traversal time. Parallel imaging is particularly important in this regard. And when you do these things, you can take images that look like this, and suddenly you have images that look like this. You convert images that are uninterpretable into images that are relatively decent in quality. So summary, you want to reduce your traversal time. Now, I talked about EPI, but let's talk now about these motion encoding gradients. What do they do? Well, the motion encoding gradients, as illustrated here, notice that I'm showing again that you can apply the motion encoding gradients, in, 3 different gradients. But let's just focus for now in one direction, and just, I could have picked any direction, but I'm going to just pick the slice encoding direction for now. What does this motion encoding gradient do? Well, the first motion encoding gradient causes dephasing of the water protons, and the water protons lose signal. The next gradient is pointing in the same direction as the first gradient. Notice that they're both pointing up over the x-axis, but it's on the other side of the 180. And because it's on the other side of the 180, it actually has the opposite effect. So this one causes dephasing, this one causes rephasing, and the water protons regain their signal. The key is that the amount of signal that is gained back depends on the motion of the water molecules. If the water molecules have moved between the dephasing gradient and the rephasing gradient, for example, if there is free diffusion, then the rephasing gradient is no longer able to rephase the dephasing because the water molecules are no longer in the same place, and you end up with a weak signal. On the other hand, if you have restricted water, for example, water that's stuck within hypercellular tissue, then the water is in a very similar location when you apply the rephasing gradient as the dephasing gradient, and the rephasing gradient is able to rephase the water and you get a strong signal. So basically, what the MEGs, what the motion encoding gradients do, is they generate contrast based on differences in water diffusion. Free water is not rephased and loses signal and therefore tends to appear dark on diffusion-weighted imaging, whereas restricted water is rephased and tends to have relatively higher signal, all other things being equal. So these motion encoding gradients generate contrast based on differences in water diffusion. Here is a T2-weighted, a diffusion-weighted image in which the gradients are not applied. This is a so-called B=0 image. And notice that we see bright structures such as bile ducts, blood vessels, cerebrospinal fluid, and ascites. When we apply the motion encoding gradients, we lose signal from the ascites, we lose signal from the water and the vessels and the ducts, and we are now able to see metastases and lymph nodes in and around the liver. Now, some people will say that in diffusion-weighted imaging, the signal of restricting tissue increases. And what I want to emphasize is that is not true. When you apply diffusion-weighted imaging, when you apply these motion encoding gradients, everything loses signal. Nothing gets brighter. However, some things lose more signal than others. You can see, for example, that the gallbladder lost more signal than the spleen, but notice that even the spleen is darker here than it was here. So when you apply diffusion-weighted imaging motion encoding gradients, everything loses signal. Now, besides the parameters that are relevant to EPI, which again are the parallel imaging, the frequency encoding matrix, and the phase encoding matrix, are there other parameters that are important in DWI? And the answer is yes. The two most important parameters are the echo time and the B value. The echo time is simply the time from the 90 to halfway through the spin echo, and I'll talk about the B value in just a minute. First question is, what is the range of echo times in clinical DWI? So notice that in different parts of the body, whether we're talking about the liver, the female pelvis, or the brain, clinical DWI uses echo times in the range of 50 milliseconds to 100 milliseconds. So therefore, you might then wonder, does that mean that clinical diffusion-weighted imaging is always T2-weighted? And the answer is yes. Clinical DWI is always T2-weighted, and in your own mind, you might think of it as a combined T2-weighted, diffusion-weighted imaging sequence. That's too much of a mouthful, so we just call it DWI. Let me skip this in the interest of time. Now, what is the B value? Because I mentioned the B value is the second parameter that's important. The B value is the diffusion sensitivity parameter. If you plot signal intensity versus the so-called B value, then you will be able to separate tissues with slow diffusion, restricted diffusion, from those with fast diffusion or free motion. Notice that restricted tissues lose signal more slowly than tissues with free diffusion. But notice again that everything loses signal. Even tissues with restricted protons lose signal. They just lose signal less rapidly. So if you are more familiar with T2 weighting, you might then benefit from this analogy. The B value is to DWI as the TE is to T2 weighted imaging. Now, what are some typical clinical ranges of B values? Well, it depends on the organ. My favorite organ is the liver. So B values that are useful in the liver include B values of 50, 400, and 800. But again, this depends on the organ. And in some organs, you might want to have B values that are considerably higher than 800. For now, I just want to point out the units of the B value, seconds per millimeter squared. You may recall that the units for diffusivity were millimeters squared per second. The B value has units that are the inverse of the diffusivity units. Now, why might I want to use a low b-value for liver imaging, such as 50 seconds per millimeter squared? You want to use a low b-value because if you don't have any b-value, if you don't have any gradients whatsoever, you have a lot of bright structures in the liver that can be confusing, bile ducts, blood vessels, etc. But a low b-value will reduce some of the signal of this background structures and make the image perhaps a little bit easier to interpret. Now, why might want to use a high b-value? The reason we want to use a high b-value is that certain tissues, for example, cancer, have very high signal on high b-value. Now, here's a low b-value image. Does anyone see the cancer in the liver? It's pretty difficult, but if I apply a high b-value, now we see that there's two separate metastases in this liver. Similar example, does anyone see the cancer in this liver on the low b-value? Some of you might have noticed this, but is there another cancer in the liver? The answer is yes, and you can see it on the high b-value. Now, why might I want to use an intermediate b-value like b equals 400? I would argue don't bother. It's a waste of time. So we're trying to move away in our practice to only two b-values, one low, one high, and we don't usually acquire intermediate b-values anymore. Well, what determines this amazing b-value? The b-value is given by this formula over here, and this formula is a little bit complicated, so let me not get into the details, but let me just point out that the b-value is a function of the gradient amplitude, so the strength of this gradient, the duration of the gradient, and the separation of the two gradients. So if you want your b-value to be higher, you either increase the amplitude, increase the duration, or increase the separation, or some combination of all three. So how does the MRI machine actually do this? Well, the first thing the machine does is it maximizes the gradient amplitude as shown over here. It then will increase the gradient duration and diffusion time until it gets to the right b-value using the formula I used there. But notice that for high b-values, it might have to move the spin echo out of the way because you can't collect the spin echo while you're applying the gradient. And so therefore, you might need to increase the echo time. Does that mean, therefore, that increasing the b-value increases the TE? And the answer is yes. Increasing the b-value usually increases the TE, which leads to signal loss and leads to low signal-to-noise imaging. So in general, you want to use the lowest echo time you can to achieve a desired b-value. Here's a case where I purposely applied a TE of 100 where I could have gotten away with a TE of 50. Parameters are otherwise identical. Notice how much better the TE equals 50 is image than the TE 100. So you want to keep your TEs short. So how can you do that? How can you keep your TE short and still get a high b-value? Well, some of the strategies are done by the manufacturers, but here's a strategy that you can do in your own practice. You apply all the gradients simultaneously. Now, why would applying all the gradients simultaneously help? The reason it helps is if you apply all the gradients simultaneously, then you end up with a net vector, which is basically the Pythagorean theorem through a three-dimensional triangle, and you end up basically amplifying the strength of the gradient by up to 1.73 times. So imagine that we apply all the gradients simultaneously. That effectively increases the amplitude of our gradient. We can now actually shorten the duration and the diffusion time because we have a more powerful amplitude, which allows us to decrease the spin echo time and decrease the echo time. Is there anything else I can do to improve my signal to noise? Yes, there's one other thing you can do. You can apply different numbers of excitation to different b-values. So a b-value of 0, the diffusion gradients are not on. This tends to be a high signal-to-noise image. Only apply 1 nex for this. For your high b-value images, these are images that are losing a lot of signal due to the application of the gradient of the diffusion gradient. So apply more nex to those. Okay, so let's review DWI acquisition basics. Diffusion is measured using a specialized sequence called diffusion-weighted imaging. DWI assesses the diffusion of water protons. It is a spin echo sequence with motion encoding gradients in EPI. EPI is very fast but prone to phase errors. The MEGs generate contrast based on differences in water diffusion. How do you optimize your sequence? Usually 2 B values is enough. You want to minimize your EPI traversal time by using low frequency resolution, low phase resolution, and applying parallel imaging. You want to minimize your TE by applying all gradients simultaneously and apply more next to high B values to get some signal to noise. Let's move on now quickly to basic principles of DWI interpretation. I will probably not be able to finish this entire last section, so I'll go for another 4 minutes or so, and then we'll stop. So DWI has 3 main purposes: lesion detection, increasing diagnostic confidence, and lesion characterization. And DWI can be applied qualitatively or quantitatively. Let's focus on qualitative lesion detection. Now, this is one of my favorite cases. This case is from 2008, so it's an old case, but it serves the principle well. This patient had a liver transplant for HCC, and CT shows a recurrent cancer here and a recurrent cancer here, so 2 recurrent cancers in this patient. Patient turned out to have a same-day MRI, and the MRI also shows 2 cancers, one here and one here, but the MRI actually shows a 3rd cancer in the liver. Does anyone see it? Well, I didn't see it initially until I saw the diffusion-weighted image, in which case the cancer is very obvious. Once I saw the cancer here, I could then see it in the arterial phase. Once I saw it in the arterial phase, I could then see it as this washout lesion with capsule on the 3-minute, and I was able to see the 3rd HCC. So DWI can be very helpful for lesion detection. It can also be useful for diagnostic confidence. Here we see an obvious mass in the liver. We see a smaller lesion here. You're pretty sure it's a cancer, but maybe you're not 100% sure. But when you see it lighting up on diffusion-weighted imaging, that can definitely increase your diagnostic confidence. Finally, lesion characterization. This is just a review of some of the beautiful pearls that Dr. Cherniak and Dr. Fowler taught us about yesterday. I'm not going to spend a lot of time on this. We have 2 patients. Each patient has a primary liver cancer. One of these is a cholangiocarcinoma. One of these is an HCC. Remember what Drs. Cherniak and Fowler taught us yesterday, that if you see a targetoid appearance, think cholangiocarcinoma. And here we see a targetoid appearance on diffusion. This is a cholangio, and this is an HCC. Let's just spend a minute or so on quantitative imaging and ask, what is the apparent diffusion coefficient? The apparent diffusion coefficient is an MRI measurement that attempts to approximate or measure or estimate the true diffusivity of the tissue. It is a biomarker. How was the ADC calculated? Well, we obtained DWI at 2 or more B values. Shown here are 3 B values. As I mentioned just a moment ago, we no longer acquire the intermediate B values, and we only acquire the low and high B values, but in this particular case, I'm showing 3 B values. So to measure the ADC, we measure the signal intensity of the structures of interest, in this case, spleen, lesion, and liver, and we plot these. And then we fit an exponential decay model with the equation shown over here, and we can calculate the ADC of the spleen, we can calculate the ADC of the lesion, and we can calculate the ADC of the liver. What I'd like to emphasize here are the units. Notice that the units of ADC are millimeters squared per second, just like diffusivity, except that we often will express it with a multiplier of 10 to the minus 3. Now, if we were to do the fitting for every pixel in the image, we would end up with an ADC map that basically displays pixel by pixel by pixel the ADC of every structure in the image. Now, Dr. Bashir and also yesterday Dr. Fowler mentioned that ADC maps are sometimes corrupted, so can you estimate the ADC without an ADC map? And the answer is yes, because this formula here can be converted into a formula here, which is actually pretty simple to do. You can just measure signal intensities and take the natural logarithm, and you can calculate the ADC in this way. But some of you might be saying that's too difficult, and this is the last thing I'll do, and then I'll stop, because I think this is a practical teaching point. Can I compare the ADCs of two tissues without calculating their exact values? And the answer is yes. So even if you don't want to calculate the ADCs because you don't want to do these natural logarithms, all you need to do is compare the ratios of signal intensities at two B values for a lesion, in this case, compared to some background such as the liver. And what you do is you just simply take the ratio of the signal loss. So the lesion went from 353 to 173. The liver went from 158 to 72. And these are pretty simple numbers. You can calculate that this is 2.04 and that the liver is 2.19. So notice that the lesion has lost less signal because it lost signal at a ratio at a factor of 2.04 than the background liver. And our interpretation, therefore, is that the lesion has relatively restricted diffusion. Well, I have elapsed my time. I have maybe 10 or 15 more slides to show, but I don't want to cut into Dr. Doe's time. And so I'd like to thank you very, very much for your attention. And I look very much forward to learning about texture analysis from Dr. Doe. Thank you.